Well, welcome back. In a previous session, we looked at blood gas transport, carriage of oxygen and CO2 by the blood, and we're now going on to look at CO2 transport in more detail, in the sense that it very much influences the acid-base balance of the body. So this session is going to be devoted to acid-base balance, and then at the end of it, I'm just going to add a little bit about oxygen transfer to the tissues. Now, why is CO2 so important in acid-base balance? Well, it turns out that the body puts out about 240 mils per minute of CO2 all day long, and this is equivalent to something like 10,000 milliequivalents per day. Whereas the kidney, which is the other organ particularly concerned with acid-base balance, only puts out about 100 milliequivalents of fixed acid. So you can see that the lung has an enormous role in acid-base balance, and furthermore, by altering ventilation, we can rapidly control the acid-base status, and that's why we're going to consider that in this series on respiratory physiology. I should say, though, that the renal people, the renal physiologists, also are very concerned with acid-base balance, and so they would also have a contribution to make. Well, now let's start by looking at a couple of definitions here. An acid is a molecule that releases hydrogen ions in solution. A base is a molecule that can accept a hydrogen ion. And a buffer is a substance that can reversibly bind hydrogen ions. So let's look at the buffering systems of the blood. The definition, as you see here, is that a hydrogen ion is taken up by a buffer, and that's given, the result is over here. And the most important buffer system in the blood is the bicarbonate system, where the hydrogen ion is combined with a bicarbonate ion to give carbonic acid. Proteins also, though, have important buffering functions, particularly hemoglobin, which is a predominant protein in the blood, and they can take part in the reaction as shown here, the hydrogen ion plus the protein, to give a combination here. And the proteins work principally through the C-terminal carboxyl ends and the N-terminal amine groups. Those are the groups that are particularly important in the protein system. There's also a phosphate system shown at the bottom here, but that is less important than the other two systems. And we're going to be concentrating on the bicarbonate system here. Now, this shows what's called the titration curve for the bicarbonate buffer system. What this shows is the pH along this axis here. And here we're showing on the left-hand side what happens when you add carbonic acid or carbon dioxide to the solution, 0 to 100%. And what happens on this side, what this side shows, is the amount of buffer in the form of bicarbonate, the amount of bicarbonate ion that you're adding to the system. And you can see that there's an S-shaped curve when you plot these two variables together. And the maximum slope is at the center of this curve here, and that's called the pK. That's the maximum buffering region where adding acid or alkali causes the smallest change in pH. And you'll notice that this point, also known as the pK for the bicarbonate system, is at a pH of about 6.1. Actually, the normal operating point in the body, of course, is 7.4. And you could argue that the system would do better if the pK were closer to 7.4. But the buffering system does pretty well as it is, and not for us to try and change it. Okay, let's look at the bicarbonate reactions in a little bit more detail here. So when carbon dioxide is combined with water, it forms carbonic acid. And it does this under the influence of the enzyme carbonic anhydrase. You remember we talked about that when we looked at blood gas transport and made the point that the red cells contain carbonic anhydrase, substantial amount, so this reaction is very fast within the red cell, but it's very slow in the plasma in the absence of the red cell because plasma does not contain carbonic anhydrase. And then the carbonic acid, of course, dissociates into a hydrogen ion and a bicarbonate ion. And we can use the law of mass action to write down an equilibrium constant, which is shown here. It's the product of these two on the right-hand side of the equation divided by this on the left-hand side. So it's the concentration of hydrogen ions times the concentration of bicarbonate ions over the concentration of carbonic acid. And for the carbonic acid, we can write the solubility of carbon dioxide times the PCO2. So that allows us to get PCO2 into the equation. Now, what do you think the solubility of CO2 is? Well, you remember when we talked about the carriage of oxygen and CO2 by the blood, we pointed out that oxygen has a solubility of 0.003 mils per deciliter per millimeter of mercury, and we said that CO2 had a solubility of 0.067 mils of CO2 per deciliter per millimeter of mercury. So you may say, what's this 0.03 doing here for solubility? Well, the answer is that we're using different units. Here we're talking in terms of millimoles per liter per millimeter of mercury. Previously we were talking in terms of mils of CO2 per deciliter of blood, and that explains the difference in the constants. So the constant we're going to be using here for the solubility is 0.03. Now we can rearrange this equation and take logarithms, and I'm not going to do that in detail, but if you do that, you end up with the equation here that the pH is equal to the pK, which we saw was 6.1 for the bicarbonate system, plus the log of the ratio of bicarbonate to carbonic acid, or in this case 0.03 times PCO2. And that's known as the Henderson-Hasselbalch equation. It's a very important equation, and we're going to be using it extensively. And incidentally, we can see immediately that if the ratio of bicarbonate to PCO2 remains constant, then the pH is going to remain constant, okay? On the other hand, if we raise the bicarbonate concentration, keeping the PCO2 constant, then the pH will rise, and by contrast, if we keep the bicarbonate concentration constant and we increase the PCO2, then the pH has to fall. And we're going to look at those processes in detail. Now, it's interesting to derive the normal pH of 7.4 from the Henderson-Hasselbalch equation, and that's just shown here. Here's the Henderson-Hasselbalch equation, pH equals pK plus the log of HCO3 bicarbonate over 0.03 times PCO2. And pK, as we saw, was 6.1. The normal bicarbonate concentration in plasma is 24 millimoles. The normal PCO2, as we know, is 40. So 0.03 times 40 gives us 1.2. So we've got 24 over 1.2, and the ratio then is 20. The log of 2 is 0.3. The log of 20 is 1.3. So now we've got the pH equals 6.1 plus 1.3 equals 7.4. Isn't that nice? That's the way the normal pH comes out of the Henderson-Hasselbalch equation when we put in the appropriate levels for bicarbonate and PCO2.